What color is this orange? Did you say orange? You'd be wrong. Let's try another one. What color is this lemon? Did you say yellow? Wrong again. Today we're going to be talking about the electromagnetic spectrum, and we're going to discover why everything you thought you knew about color is wrong. I'm Mr. Wilson. Welcome to class. So let me ask you one more question. What color is the sun? You know what's interesting is that whenever I ask my students what color is an orange, I universally get the answer orange. But when I ask them what color the sun is, I get all kinds of different answers. Some say yellow, some say red, some say orange. The answer is the sun is actually white. How do we know this? I have a special filter that allows me to take a picture of the sun, and we will see that indeed it is white. So why do my students think it's all those other different colors? When you look at an orange, you can clearly see that it's orange, but when you look at the sun, well, you can't look at the sun, can you? If you did, it would burn out your eyeballs. The only time that you can really look at the sun is during the evening or early morning when the sun is still low on the horizon. And indeed, when you look at the sun during those early morning or late evening hours, it looks orange or red or yellow. So it turns out that objects don't actually have color at all. All of the color is contained in the light. And when we talk about white light actually contains all of the colors all at once. So when we look at an object and it looks like it's orange, what's actually happening is all of the colors are hitting this object at the same time, and this object is absorbing all of those colors except for orange. So the white light hits it and only orange gets reflected back to your eyes, and therefore your eyes perceive this object as being orange. And it's that way with everything. If we look at a lemon and it looks yellow, what's actually happening is the white light is hitting that object is absorbing all of the colors except for yellow, and yellow gets reflected back to your eyes. Therefore, you perceive it as yellow. So what we find out is that objects don't actually have color at all. All the color is coming from the light itself.
Now this is actually kind of weird. In order for me to properly explain what's going on here, I have to use some equipment that I left in my classroom. And it's weird because of the pandemic. This is actually the first time I'll have been to my classroom in almost a year.
Kind of weird. I haven't been here in a year. So we've learned that white light contains all of the colors. But is there some way to prove it? Actually, yes. Since all of the wavelengths of color are all coming into your eye at the same time, we perceive them as white. But if we could spread those wavelengths out, we would see a rainbow. But how do you do that? How do you spread that light out to see the individual colors? It turns out when light passes through a transparent or translucent medium, that automatically happens. The type of substance and its density both impact this effect. Here I have a piece of plexiglass, and you can see that all of the edges are transparent, and then one side has been sanded down to give it a rough finish. Now this shape is irregular, but it is important to note that this side and this side are parallel. So if I pass a beam of light straight through this, you intuitively would think that that beam of light would come straight out the bottom. But because that light is passing through a substance, it will be, to a certain extent, bent. So here, if we look at this, if I turn this so that this side and this side faces the camera like this, we're now looking through one side and out the parallel side. I'm going to take this object, which is quite straight, and put it in front of this, and you will see that that light is being bent. Let's use a little demonstration to figure out what exactly is going on here. So what I have are 3 boxes, and each one of these boxes has a light bulb in it, just a light bulb generating plain white light. Now I put this little filter, this little plastic piece in front of it, and it will allow me to create little slits of light or one larger slit of light like this. So when we put this in front of here, we get a nice beam of light. Here's our light box again, but this time I'm going to use a different side of my plastic filter. I'm going to use this side that has a series of little slits. That's going to generate several parallel lines. As we learned before, if the light is passing through one side and comes out another side that is parallel to it, a little bit of bending may take place, but for the most part, not a whole lot of change will be visible. As I put the lens in place, we can see that that is confirmed. The light passes through one side and comes out the other side, for the most part unaffected. However, if I move this over a little bit so that some of these beams are actually hitting the angled edge of the lens, the light will bounce off of that edge and move in a different direction and come out the side over here. The angle at which that light is reflecting off of the one side and bouncing off the other will determine how much that light is going to be bent. Here we have a concave lens. If I put this in front of my light, we can see that each beam is bent outward. We call this scattering. Here we have a convex lens. If I place this in front of my light, we can see that the light is bent inward and is focused to a point out here. As we saw before, if I tilt the lens, then the light will impact the various edges at different points, and it will be scattered in different ways. So it's important to keep the angle of the lens perpendicular to the path of the light if you want to focus at an exact point. When we're talking about cameras, we would say that this is the focal plane. All of the light is passing through the camera's lens and bent toward the camera's sensor here. If the camera's sensor is located here, your image will be in focus. If the camera's sensor is located anywhere else, your image will be blurry. You can move the lens backward and forward to change the location of your focal plane. This is how a camera focuses its image. Here I have a triangular piece of plastic. This is a right triangle, so these two edges are perpendicular to each other, or at a 90-degree angle. By placing the prism in this orientation, we can see that the beam of light is traveling out, bouncing off of this 45-degree angle, and exiting this face at 90 degrees. Telescope eyepieces make use of a prism like this to redirect the light coming from the telescope into your eyepiece so that you can view it at a more comfortable angle. Here we're using another triangular piece of glass, but this time all edges are the same length and all angles are the same. We call this an equilateral triangle. By rotating it at just the right angle, the light will pass in one face and be bent to another, and reflected off in various directions as you see here. What's interesting is what is happening to the light that is passing out of this face. If you look closely, you'll see that the light coming out at these various angles is still white. That means all of the wavelengths are traveling in the same direction. But what's happening out of this angle is a little bit different. Here, each wavelength is exiting the prism at a slightly different angle. That separates the wavelengths, and as we get out further away from the prism, you can start to see a rainbow effect happening here. This proves that white light actually contains all of the colors of the rainbow, and that if we bend those colors, we can separate them and make their respective colors visible. So at this point, you may be thinking, wait a minute, if light contains all of the colors, then that means it contains blue and yellow, and I know that when I mix blue and yellow, I get green. And if I mix green with red, I start getting, I don't know, some kind of ugly brown color or something. And then more colors I mix, the closer it gets to black. So isn't black the one that contains all of the colors? No, because you're thinking about mixing paint and mixing light are two totally different concepts. Let's take a look at the visible light spectrum. These are the colors that we can see with the naked eye. Do you notice two colors are missing? There is no white or black present anywhere in this rainbow. That means there's something special about white and black that doesn't apply to any of the other colors. So before we talk about the differences between light and paint and white and black, let's discuss what color is made of, that is to say, how it actually works. Visible light is a small part of a larger field of energy called the electromagnetic spectrum. Electromagnetic energy travels in the form of a wave. In order to understand the EM spectrum, you need to understand some key vocabulary related to waves. The highest point of the wave is called the peak or crest, and the lowest point of the wave is called the trough. The vertical distance from the peak to the trough is called the amplitude. And most importantly, the distance from one peak to another is the wavelength. If you've ever seen a ripple on a pond, you know the crests of these waves move. If I were to count how many crests pass by a given point in 1 second, that would be called the frequency, and it's measured in hertz. For example, if we see that 2 wave crests pass by in 1 second, we would say that the wave has a frequency of 2 hertz. If 2 million crests pass by in a second, we would say that the wave has a frequency of 2 million hertz, although we usually simplify it as 2 megahertz. Here we see 2 different waves. The amplitude or vertical height from crest to trough is the same with each wave, but look at the top wave. Do you see how the wavelength or distance from one crest to another is shorter? Now look at the bottom wave and notice the distance between the crests is comparatively longer. If an electromagnetic wavelength is long, say the size of a football field, we call it AM radio. If the wave is shorter, say the length of your arm, we call it FM radio. Shorter still, and we start moving into the infrared end of the spectrum. Now, we can't see any of these wavelengths with our own eyes, but we can build devices to detect them. The radio in your car is an example of such a device. When it comes to infrared, that one you can't see, but you can feel it. The warmth of the sun on your skin is how our brain interprets infrared electromagnetic radiation exciting the molecules that make up your skin cells. As we continue to shrink the wavelength, we start to get into the visible end of the spectrum. This is the part that our eyes can actually see. The visible range of the EM spectrum starts with waves that have a length of only around 700 nanometers. A nanometer is 1 billionth of a meter. Now that's incredibly small. To put that in perspective, a human hair has an average diameter of 50,000 nanometers. So the length of the largest wave in the visible light spectrum is 71 times smaller than a human hair, and the wavelengths just get smaller from there. Now you obviously wouldn't be able to see an object that was that small with your own eyes, but our eyes are tuned to these frequencies and they can detect even the slightest differences in the wavelengths. And it is the length of these waves that our brain interprets as color. Longer waves are interpreted as red, and as the wavelengths get shorter, we start to interpret them as different colors, such as orange, yellow, green, and all the way through the rainbow. Eventually, the wavelengths become so short, however, that we once again can't see them, and that's when we start getting into the ultraviolet and X-ray end of the EM spectrum. So if we compare the red to the orange, the wavelengths of these, 650 versus 590, that's not a lot of difference for something that is so small. And yet our eyes and our brain are so sensitive that they can detect such a slight difference in such a small wavelength. And our brains interpret that as totally different colors. You can see I have 3 of these, and each one of the beams of light is converging onto this little white piece of plastic. You can see just a white piece of plastic here. Put that there. So the color of all 3 lights is converging into that one point. Now what I have are these little pieces of transparent colored plastic. These are called gels. And I can put these little gels in front of the beams of light to change their color. So here I've got a yellow one. Here I'll put a blue one. And we'll put a red one in the middle. Now, it doesn't matter which order I put these in as long as I have all 3. Now you can see that all 3 of these individual colors are all converging into that one place. So the 3 colors are mixing. Now I don't have every color of the rainbow, just 3. So I'm not going to get pure white light here, but I am going to start to see hints of white light. Let's go ahead and zoom in to see if we can see it a little bit more clearly. You can see right here at the bottom of the plastic panel here that it is starting to get a little bit more white, at least compared to the 3 colors that are coming in. So you can see if I, for example, if I move the red and the yellow away, you can see that is just red. And if I bring in the blue light, you can see that this blue light here, when it starts to mix with the red light, it is starting to get a little bit lighter in color there at the bottom. And when I do the same thing, adding the 3rd color, you can see it's starting to get actually quite a bit lighter at the bottom of the plastic panel. Now if I were to swap out one of the colors, let's say that I swap out the blue one for this orange one, you'll see that we'll lose a lot of that effect. This means that all of the colors in the electromagnetic spectrum are primarily represented on the longer wavelengths. Because I don't have any representation on the shorter wavelengths, I'm not getting nearly as much of the white at the bottom as I was before. So now let's get back to that paint example we were talking about before. And let's start thinking about what blue paint really is. It's a substance specifically formulated to absorb all of the wavelengths except for blue. The blue light is reflected back at the observer. A yellow paint absorbs all of the colors except for yellow. Most paints aren't going to do this perfectly. The yellow one, for example, is going to reflect mostly yellow, but there will be a little bit of other colors in there too. Likewise for blue. So when you mix the two, the yellow one is going to absorb the wavelengths that the blue one is trying to reflect, and vice versa. So what you're left with is only the little bits of color that both reflect in common. In this case, mostly green. Okay, so we know how paint works now, and we know why mixing different paint colors doesn't get you white, but what if I mix all of the paint colors and end up with black? What's that about? And why, for that matter, is black not a color on the rainbow? Remember that white light contains all of the colors all at once. Seeing so many different wavelengths coming at your eyes all at once essentially overloads your brain. It can't make out that many colors all at the same time, so it just perceives such a situation as white. When white light hits something that we perceive to be black, that thing is actually absorbing all of the color wavelengths and reflecting back very little. So what your eyes are actually seeing is a lack of reflected color, and your brain interprets such a lack of color as black. Perhaps now we can see why mixing all of the paint colors together starts to give you black. Remember, Each color is designed to absorb all of the colors except for the one that they're formulated for, so let's say blue. But the yellow you mixed in with it is going to absorb the blue light that the blue paint is trying to reflect. Maybe there's a little overlap between the two, so you get some green, but then you mixed in red. And the red is going to absorb the green light too. The more paints you mix in, the more colors you are absorbing, and the closer you get to black, wherein very few wavelengths are reflected at all. So let's talk about why the sun starts to look yellow and orange and red at sunset or in the morning at sunrise. So what's going on here is this is the Earth, and this circle around it is our atmosphere. We're going to say that this is you at the top of the planet looking at the sun, and the sun is going to be out over here like this. Now, light from the sun is traveling through space to get to our planet. When it hits our atmosphere, this is at sunset time, so the sun is low on the horizon. So you can see that the sunlight has to travel through this much atmosphere to make it to your eyes. But if the sun is now, let's say, directly overhead, like at noon, the sunlight is again traveling through space. It hits our atmosphere. This time the sunlight only has to travel through this much atmosphere to get to your eyes. So you can see that in the evening and in the morning, when the sun is low on the horizon, the sunlight has to travel through far more atmosphere than it does during the middle of the day. So why is that relevant? Why does that matter? It turns out that our atmosphere is quite dirty. It's full of water vapor, it's full of dust and debris and all kinds of stuff. And as the sunlight is passing through all of that debris, it is scattered in all different directions. And that scattering effect affects some wavelengths more than others. And in this case, the majority of the wavelengths that are scattered are all the different colors of the rainbow except for the orange and the red. The longer wavelengths are the ones that are best at cutting through all of that debris and actually making it to your eyes. During midday, when the sunlight is passing through the atmosphere, there's not nearly as much dirt and material that it has to pass through, and the light is scattered to a much less effect. And it turns out that the blue light is really scattered the most, which explains why the sky is blue, and all of the rest of the colors can make it to our eyes. Since primarily the blue is the only stuff that's filtered out and all of those other colors are making it to your eyes, we perceive most of the colors of the rainbow, and therefore it looks like white light to us. So there you go. Now you understand what color is. This is what I really like about science. Anyone can memorize a factoid about wavelengths or color or what have you, but to truly understand the concept and what is going on in the world around us gives us insight that most people just take for granted. And that level of understanding, I think, is something really special. And I hope you do too.